far beyond the stars we recognize in our night sky. Within a quiet stretch of the constellation Leo, a subtle shift in infrared light finally reached Earth. That signal had spent more than 100 years crossing the dark emptiness of space. At first, it appeared ordinary, just another data set, another ribbon of numbers among the countless streams gathered by humanity's most advanced telescope. But embedded within that light was something entirely unexpected. A chemical fingerprint that does not originate from rock, water, or weather, but from life itself. The James Webb Space Telescope had identified a world so precisely balanced, so chemically active, that scientists reached a level of confidence rarely achieved in astronomy. This was not speculation, not probability. It was a planet that appears fully habitable, and possibly even more life-friendly than Earth. What Webb uncovered does not merely hint that life could exist somewhere in the cosmos. It suggests we may have finally found it. The discovery did not arrive with fanfare. It was hidden deep within infrared observations collected as a distant planet passed in front of its star. As that starlight filtered through the planet's atmosphere, certain wavelengths vanished, leaving behind a unique spectral signature. At first, researchers identified familiar compounds: water vapor, methane, carbon dioxide, each meaningful, each suggestive. Then came a molecule that changed everything: dimethyl sulfide. On Earth, this compound is produced exclusively by living organisms, not by volcanoes, not by lightning, not by chemistry alone, by life. And the signal was strong. So strong that the chance of error fell below 3 in 1,000. In a field defined by uncertainty, that level of confidence is extraordinary. The planet, known as K218b, orbits a red dwarf star roughly 120 light-years away, squarely within the region where liquid water can exist. But unlike the rocky, Earth-like planet scientists once believed were required for life, this world belongs to an entirely different category. It is a super-Earth, larger, heavier, and wrapped in a thick, hydrogen-rich atmosphere. And rather than making it hostile, that atmosphere may be exactly what makes it ideal. K218b is not balanced precariously the way Earth is. Its environment appears remarkably stable. Surface temperatures hover near 120 degrees Fahrenheit, warm enough for liquid water, yet cool enough to prevent oceans from evaporating. This warmth is no accident. The hydrogen-rich atmosphere functions like a planetary blanket, trapping heat and distributing it evenly around the globe. Unlike Earth, with its dramatic swings between day and night, summer and winter, this planet may experience consistent, planet-wide conditions. Even the permanently dark night side, locked in place by tidal forces, remains warm enough to sustain liquid water. Gravity plays a critical role. With nearly 3 times Earth's surface gravity, K218b retains its atmosphere with ease, preventing the slow atmospheric loss that stripped Mars billions of years ago. What appears extreme to us may actually be advantageous. Strong gravity, a dense atmosphere, stable temperatures. Together, these factors create an environment where life does not need to constantly struggle for survival, but can instead focus on growth, complexity, and evolution across immense spans of time. The star that hosts this planet is a red dwarf, smaller and cooler than our Sun, yet vastly more enduring. While our Sun will one day expand and erase all life on Earth, red dwarfs burn steadily for trillions of years. That means any life that arises on a planet like K218b is granted an almost unlimited evolutionary timeline. The planet completes an orbit every 33 days, sitting close to its star while receiving nearly the same energy per square meter that Earth receives from the Sun. It lies firmly within the habitable zone, but with one crucial difference. Around red dwarfs, that zone lasts far longer than around stars like ours. Add the planet's thick atmosphere, which shields the surface from radiation and redistributes heat globally, and it becomes clear why scientists are rethinking everything they once believed about habitability. This discovery suggests that Earth-like planets may not be the optimal places to search for life. Instead, the universe may favor worlds that are larger, warmer, and far more stable than our own. What elevates this discovery even further is the behavior of K2-18b's atmosphere. The detected gases exist in a state of chemical imbalance. In a lifeless environment, these molecules would react with one another and disappear. Yet they persist in significant quantities. On Earth, this kind of atmospheric disequilibrium is sustained only by biological processes. Life continuously injects gases into the atmosphere, preventing it from settling into chemical equilibrium. K2-18b exhibits the same pattern. The absence of ammonia, a compound expected in lifeless, hydrogen-rich atmospheres, strengthens the case even more. Something appears to be actively removing it. Something alive. If this interpretation is correct, then we are not observing a planet where life might emerge someday. We are witnessing a planet where life is already shaping its environment on a global scale. A living world breathing across interstellar space, detectable from 120 light-years away. For decades, the search for life beyond Earth followed a strict template. Scientists believed they needed a near-perfect Earth twin, similar size, similar mass, thin atmosphere, rocky surface, sun-like star. K2-18b shattered that framework in a single discovery. This is not Earth's twin. It is Earth's oversized, unfamiliar cousin, operating under conditions once assumed to be hostile to biology. With more than 8 times Earth's mass, K2-18b belongs to a class of planets known as super-Earths, worlds long dismissed as bloated, gas-heavy, and inhospitable. Yet the data tells a different story. The planet's immense gravity acts as a stabilizer, anchoring its atmosphere and preventing the erosion that doomed Mars. Its thick hydrogen envelope, once considered incompatible with life, instead creates a stable thermal environment that preserves liquid water across the planet. This forces a fundamental shift in perspective. Habitability may not depend on fragility or perfect balance. It may depend on resilience, mass, and long-term stability. K2-18b suggests that the most life-friendly world in the galaxy are not delicate replicas of Earth, but robust planets designed to endure for trillions of years. Beneath K2-18b's hydrogen-rich skies may lie one of the most extraordinary environments ever discovered. Vast, global oceans potentially hundreds of miles deep, composed of water mixed with dissolved hydrogen under immense pressure. This is not an Earth-like ocean confined to shallow basins. This is a planetary ocean, a continuous liquid world that dwarfs every ocean in our solar system combined. Hydrogen fundamentally alters how this ocean behaves. Dissolved hydrogen expands the temperature and pressure range in which liquid water can exist, allowing stability far beyond Earth's limits. Where extreme pressure collapses biological structures on Earth, hydrogen on K2-18b may act as a buffer, maintaining conditions suitable for chemistry and potentially life at staggering depths. This opens the door to ecosystems of unimaginable scale. Life would not be limited to coastlines or surface waters. Entire biospheres could exist layered through the depths, thriving in warm, chemically rich environments where energy is abundant and stable. In such an ocean, evolution would not be constrained by scarcity. It would be accelerated by abundance. Perhaps the most unsettling implication of Webb's observations is the sheer strength of the biosignatures detected. Dimethyl sulfide does not linger quietly. It breaks down rapidly under stellar radiation. On Earth, its presence requires constant replenishment by living organisms, primarily across vast oceans. For Webb to detect it from 120 light-years away, biological activity on K2-18b cannot be localized. It must be planetary. This is not a world where life survives in isolated pockets. It is a world where life dominates atmospheric chemistry. The concentrations imply a biosphere operating at a scale far beyond anything humanity has experienced. Entire oceans breathing, metabolizing, and continuously reshaping the atmosphere. This is not a faint microbial whisper. is the roar of a thriving planetary ecosystem. K218b does not merely host life. It is shaped by it. The implications extend far beyond a single planet. Red dwarf stars make up roughly 3/4 of all stars in the Milky Way. If even a fraction of their planets resemble K218b, the number of potentially habitable worlds increases not by tens, but by hundreds. Worlds once dismissed as too massive, too hydrogen-rich, too alien are suddenly reclassified as prime candidates for life. The universe may not be sparsely populated with rare, Earth-like oases. It may be densely filled with super-Earth water worlds, each wrapped in thick atmospheres, each stable for trillions of years, each capable of hosting biospheres far more mature than Earth's. The discovery of K218b forces a radical conclusion. Life may not be rare. It may be the default outcome wherever physics allows stability, water, and time. And the James Webb Space Telescope has given humanity its first clear glimpse of that reality. For years, hydrogen-rich atmospheres were considered dead ends in the search for life. Hydrogen was thought too light, too reactive, too unstable. On Earth, it escapes almost immediately. On K218b, hydrogen does the opposite. It dominates, forming a massive envelope that reshapes the planet's climate and chemistry. This atmosphere does more than hover above the surface. It actively regulates temperature, pressure, and radiation exposure. By trapping infrared heat with remarkable efficiency, it erases extreme temperature gradients. Day and night blur together. Seasons lose significance. The planet remains relentlessly habitable. In this environment, life is not constantly stressed. It is free to optimize, diversify, and grow complex. The hydrogen atmosphere, once labeled hostile, emerges as the ultimate stabilizer, a planetary incubator designed not for survival, but for flourishing. The chemistry of K218b's atmosphere tells a deeper story. Methane, carbon dioxide, water vapor, and dimethyl sulfide coexist in combinations that should not persist without life. In a lifeless world, equilibrium would prevail. Here, equilibrium never arrives. Something continuously injects energy and matter back into the system. On Earth, that role belongs to biology. K218b shows the same signature, but on a far larger scale. Life is not a passenger on this planet. It is the engine. The atmosphere behaves less like a shell and more like a metabolic organ, processing chemicals in real time as a planetary biosphere breathes beneath it. Every transit observed by Webb reinforces this picture. This is not a planet waiting for life. It is a planet where life has already taken control. Time may be the most underestimated factor in the emergence of complex life. Earth is 4.5 billion years old, yet complex life appeared only recently. K218b exists in a radically different temporal context. Its star will burn for trillions of years. Its habitable conditions are not fleeting. They are effectively permanent. Evolution on K218b is not racing against extinction. It is unfolding slowly, deliberately. With stable temperatures, vast oceans, and immense time, life can explore evolutionary pathways Earth never had time to attempt. K218b is not just habitable today. It may have been habitable for billions of years, and may remain so long after Earth is gone. The detection of K218b marks a turning point, not because it answers every question, but because it changes the question itself. The search is no longer about whether life exists elsewhere. It is about how common it truly is. Webb has not merely detected a habitable planet. It has revealed a universe that may be optimized for life. A universe where Earth is not the template, but the exception. If this discovery changed the way you see the night sky, make sure to like this video, subscribe to the channel, and share it with anyone who still believes the universe is empty. Because from this moment on, every star carries a new question. Not whether life exists out there, but how much of it is already waiting to be found. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.